Chapter 8, Section 1. Exciting because we are going to begin to get into something called trigonometry. Now, that may be a big word. It is really not hard. We don't do any trigonometry today, but we get into it in this chapter. Trigonometry, the prefix to that just comes from triangle. And metrics for trigonometry, the metrics is it measures, it's triangle measure. You guys have been measuring triangles all year long, so it's not going to be hard, but it may just be new. All right. Mean. We have used the word mean in math, or you have used the word mean in math, hopefully for several years. We're not talking about somebody who is unkind. We are talking about average. It's an average. There is an arithmetic mean, that is the, quotes, average that you are used to, where you add all the numbers up and divide by how many you have. There is also something called a geometric mean. It is its own kind of average. And the geometric mean comes from a proportion. And we have been working with proportions. And we have learned that the extremes are the very first and very last things that are written in a proportion. A to x equals x to b. A and b are the extremes. And the means are the middle values. And if those middle values are the same thing, notice right here, x is in both positions, then that number or that value is called the geometric mean. So a geometric mean relationship are those middle values. Now let's do some cross products a minute. If I started with the means and said x times x, or x squared, I know that would equal a times b. What would we do to solve for x instead of x squared up there?
X equals the square root of a.
Square root. In order to get rid of the square, we'd take the square root. Square root of a times b. There is a formula for finding a geometric mean between two numbers. Because x is the same, the mean's position is the same value, then it becomes squared. To get rid of it, you just take the square root of the product of the other two. That's what they have shown right here. If I take the cross products, and then if I solve for x, and we just take the positive square root, even though mathematically there's both a positive and a negative answer to x squared equals ab, we just take the positive square root because we are referring to a geometric length, a positive length here. So if they want the geometric mean of 9 and 4, well, notice what they did. They got 6 because the square root of 9 times 4 is 6. What's 9 times 4? 36. What's the square root of 36? 6. Geometric mean between 9 and 4 is 6. It's not the arithmetic mean, which is you would add them together and divide by 2. It's the geometric mean. So, easy enough. Let's find the geometric mean between these numbers, 5 and 45. Well, the geometric mean would equal the square root of 5 times 45, which is, if you need to, you can use a calculator. I'll close my eyes while I see you get it out. How much? What's 5 times 45? 225. And then if you take the square root of 225, you get an integer. You get 15. So 15 would be the geometric mean. Let's try these, 12 and 15. If I want the geometric mean, well, it's the square root of 12 times 15. What is 12 times 15?
180.
180. How about the square root of 180? Is it an integer? I need to simplify it. It's not an integer. So if I simplify it, I need to look for a perfect square that goes into 180. Remember what we mean when we say perfect squares? 4 is a perfect square. What's the square root of 4? 2. What's the 9 is a perfect square? What's the next one? 16, 25, 36, dot, dot, dot. How do you get perfect squares? Square 2, 4. There's the first one that's useful to us. Square 3, 9. Square 4, 16. Square 5, 25. Square 6, 36. That's how you can get perfect squares. What's the biggest one that goes into 180? 36? How many times? Try that. Does 36 go into 180? 5 times exactly. So, we have done this before. This can be written as the square root of 36 times the square root of 5, and the square root of 36, Andrew, is the number? 6. square roots of 5. That's the answer. Now there's a decimal approximation. It's approximately, I don't know, if you take the square root of 180, what decimal do you get? 13 point something? Okay, there's a decimal approximation, but this is the exact value. Be able to get the exact value. Approximately 13 point. Use a calculator. 13 point, goes to 14?
41.
Oh, sorry, didn't understand. 13.4, approximately. If an altitude, what is an altitude in a triangle?
It goes from a point to straight up.
Goes from
The highest point.
maybe the highest point. Doesn't have to be an altitude. It goes from a vertex, and then what else? Perpendicular to the opposite side. An altitude goes from a vertex perpendicular to the opposite side. There are 3 altitudes in any triangle, because you can go from any vertex perpendicular to the line containing the opposite side. An altitude drawn to the hypotenuse of a right triangle. So they are saying here that we have a right triangle. So ABC was a right triangle. And they take an altitude to the hypotenuse, so it's only one specific altitude of the right triangle. Since it's an altitude, it also hits perpendicular. Then the 2 triangles formed are similar to the original triangle and to each other. So this theorem says if I have a right triangle, I draw the altitude to the hypotenuse, so it'll be the one that comes from the right angle to the hypotenuse. Then I've divided it into 2 triangles. Those 2 triangles are similar to the original, and they are similar to each other. So they have listed it out, and let's make sure we can follow and get the letters in the right order. Triangle ABC was the original right triangle. So ABC was the original right triangle. If I'm going to make it similar to this big one on the left, well, angle A still matches with angle A. It's the same angle. Angle C was the right angle. So when ABC, I need to end with my right angle. So it needs to be ACD would be the order. So there you can see triangle ACD, so that I keep my corresponding angles, my congruent angles matched up. Let's try it with the small triangle on the right. If I had ABC, well, angle A and angle C are the smallest angles that now match up. So it would be C, and then it would be B, CDB. ABC ends with the right angle, so I need to end with the right angle. CBD. CBD, there we go. CBD is where they ended with it. And then you'd have to match up these 2 little ones together. Underlined the wrong one first, didn't I? So if they said ACD, that would be CBD. ACD and CBD. It's important to remember the order that our letters go when we're talking about similar triangles. So using that theorem, here they are saying in this example, to write and simplify statements identifying the 3 similar right triangles in the figure. So, see if I can cover it up real quick. If, had that answer sitting out there. If I did this, I could say, all right, the original triangle, I'm going to call it FGH. Triangle FGH must be similar to triangle. Now, how I did this one, F, which is, if I look at the relative size, F is the larger of the 2 acute angles, then G is the right angle, and then our third one over here, FGH. So if I'm going to do it with the FJG thing, the little one up here, well, F matches with what in the little blue one on this one? F matches with F. It's the same angle. F in the large triangle is the same angle as F in this small triangle, so F matches with F. If in the big I said F to G, which is the right angle, well then in this little one I need to see F to J, F to J, F to J, and then it's easy, we just fill it in with the last letter, FJG. That would be the similarity in that one. If I did the same order for this middle one, and I may be doing it different than theirs, FGH, the big one, triangle FGH, similar to triangle, okay, now GJH, GJH, we're talking about the red one on the right, the big one once we split it into two. So angle F up here, which angle would it match with in this one? It would match with G, that's the larger of the two. It would match with G. So I need to start G, and then remember I want FG, the right angle. So over here I need to go G, J, the right angle. G, J, H. You can just throw in the last letter. That's easy to do. This one over here, FGH, what is that? Oh, that's the big one, FGH. I already made that one. If I want to correspond these two, let me take a different order. I'm going to say triangle FGJ. FGJ would be similar to triangle G, HJ. I want FGH, F to the other acute, ended with my right, G to the other acute, H, end with my right, J. Just match them up correctly. So let's try it out down here. 2A, we are going to do the same thing. I am going to start by the big triangle, and I'm going to say KML. Now, I guess before I even do that, we need to make sure this is the right kind of altitude that was drawn. The altitude has to be the altitude drawn to what did it say in the theorem? The hypotenuse of that original. So the original KML is a right triangle. Here's the right angle. So we know the hypotenuse is the one across from the right angle. So make sure you keep that relationship in mind. It's going from a vertex, an altitude drawn to the hypotenuse, which it is. All right, similar to, switch my color. Similar to triangle, I want to do the one on the left. What matches up with K on the little one on the left? I think I heard it. K. It's the same angle. K matches with K. K. Now if I come back here, M in the big one was which angle in the big triangle? The right angle. So what's the right angle on the little one on the left? P. And then I'd end up with what? M. KPM. So if I use KML again, and I'm going to do to the one on the right, triangle KML, it'd be similar to triangle. Now we need to figure out which one matches with K. It's M is the one that matches. Now I want to see why. Why is this one that's going to match up with M? Remember that our two acute angles are going to add up to 90 degrees. So this angle, the K angle, and this L angle up here are going to be my 90 degrees that come together. Is this explanation going to help you? Not sure if this explanation is going to help you or not. Well, I don't think what I was going to say is going to be very helpful to you. You look at the relative size, and whether you're looking at K is right beside the short leg, M is beside the shorter leg. Whoa, M is beside the shorter leg of this other one. Or you can maybe look at the relative size of the angles. K and M, those are the ones that always match up. Okay, M in the original, again, is the right, so what goes next here? P is the right in the other one, and then L is my last one. And then if I did between these two, the two small ones, I could say triangle K, let's say I said KPM. KPM, the little one on the left. Similar to triangle, MPL. M, that's the one that matches with the K. P is the right angle still, and then it finishes up L. I won't do number 28, it's the same idea, we've done two of them. But just make sure you match up the correct pieces. From this, let's look at what can happen. Here they have taken the original triangle, ABC. They have taken the small triangle on the left, that DAC, or whatever order it happens to be, and then they have the small triangle on the right, and they have written proportions from it. Now, if I go to this original triangle, ABC, across from angle A is side A, and we continue with that. That's how we traditionally write our triangles. Across from angle B is going to be side B over here, and across from angle C, which is the right angle of the original, there's my side C. So our lowercase c, our lowercase a, b, and c are the side lengths for angles, capital A, B, and C. So on this first one down here on the left, that's all it is. Then the little one on the right, on the left, well, they are calling x, this bottom side, and h, the height or the altitude of it. And so they just wrote a proportion where they took shorter leg to longer leg. So in the original triangle, shorter leg to longer leg, B to A, B to A. And then they finished it up with the other two, shorter leg to longer leg, x to h in the little one, and h to y in the big one, using these letters that they set up at the beginning. And so they have circled now the last two. We'll come back and look at that in a minute. Then they did a hypotenuse to shorter leg. They're doing all three types of ratios we can get. So hypotenuse to shorter leg, well, C to B in the original, C to B. So C to B. And then hypotenuse to shorter leg, B to X, B to X. Hypotenuse to shorter leg, A to H, A to H. And they happen to circle these two this time. They're just taking parts of these proportions. And then they did hypotenuse to longer leg. So C to A in the original, C to A. Then they did A to H in the middle one. Sorry, B to H in the middle. And then A to Y in the last one. And then they have combined these two right over here. Let's look at the means position. Is it the same value in this first proportion? Yeah. Which means whatever they're talking about in that means position, that is a geometric mean between x and y. H. What was the H? Let's come up here. The H was the altitude. The altitude is a geometric mean between x and y. The segments of this hypotenuse. When I have a right triangle and I draw an altitude to hypotenuse, that altitude is a geometric mean between the segments of the hypotenuse that we just created. That's what this says. Let's try the next one. Notice this also has the same value in the means position. The B value is a geometric mean between whatever C and X is. Well, where did the B value come from? The B value was the short leg of the original. C and X. C was the whole hypotenuse, and X is that piece of the hypotenuse that's right next to that leg. A leg of the original is a geometric mean between the whole hypotenuse and the segment of the hypotenuse next to that leg. We're going to see that that comes true right over here again. Look at this one. A and A is in the means position and what they have circled. So where was A? A was a leg of the original again. And it's between C and Y. C is the whole hypotenuse, and Y is the segment of the hypotenuse next to that leg. These last two proportions yield the same geometric mean relationship. A leg of the original is the geometric mean between the whole hypotenuse and the segment of the hypotenuse next to the leg. Now I'm going to repeat it with this A. A leg of the original A is a geometric mean between the whole hypotenuse and the segment of the hypotenuse adjacent to that leg. These last two are the same words for the same geometric mean relationship. And this first one, the altitude, is a geometric mean between these two segments. That is formally stated in this theorem right down here, these two theorems. Right triangle geometric mean theorems. Let's read this first one. The altitude one. The altitude drawn to the hypotenuse, the altitude drawn to the hypotenuse of a right triangle separates the hypotenuse into two segments. The lengths of this altitude is the geometric mean between these two segment lengths. B, or H, the height, the altitude, is the geometric mean between the X and the Y. I prefer, when we work with the triangles, to use the proportion to help me figure out what I'm trying to solve instead of this formula. The formula is still correct, but I found that in the figures we work with, setting up the proportion is usually easier for students to do. So that's how I'm going to work with it, even though that equation, geometric mean equation, is still true. The second one, the geometric mean leg theorem. If I have an altitude drawn to the hypotenuse of a right triangle, it separates the hypotenuse into two segments. So far, everything looks the same. But what is different now is the length of a leg of the triangle. The length of a leg of the triangle is the geometric mean between the length of the whole hypotenuse and the segment of the hypotenuse that's adjacent or next to that leg. Same thing works with the B. A leg of a leg of the original is the geometric mean between the whole hypotenuse and the segment of the hypotenuse next to that leg. So they have set up, again, a proportion. And the geometric mean is what goes in the means position. B went in the means position. A went in the means position. First one, H went in the means position. Very, very important. Make sure you're very comfortable with those two theorems. So let's practice them just a little bit over here. See if we can make it work. So here we have a right triangle. An altitude was drawn to the hypotenuse of that right triangle. Therefore, we have some geometric means. They say, figure out what X is over here. All right, well, X is that altitude. So I know X is a geometric mean. I am going to place it in the means position. And it's the geometric mean for what? The segments of the hypotenuse, this 20 and this 5. And it doesn't matter whether you said it's between the 20 and the 5 or the 5 and the 20. We would get the same answer. X squared would equal what? 100? So what would X equal? X would be 10. X must be 10. So I just figured out this thing is 10. If I want to solve for Y, well, looking down here, Y. Y is the leg of the original. So Y is a geometric mean. Y goes in the means position. So I'm filling in my proportion with the Y in the means position. Between what? Between the whole hypotenuse and the segment of the hypotenuse next to the leg. 25 and 5. And again, it wouldn't matter if you said between 25 and 5 or 5 and 25. You'd get the same answer. Y squared would equal what? 5 times 25. 125. So in order to get Y, what do I have to do? What do I have to do to get Y? Is that a Y squared? Square root of 125. Is that an integer? No. So I'm looking for a perfect square that goes into 125, preferably the largest one. How much? 25. How many times? 5 times. You can think of where we got this number. What is the square root of 25? 5 square roots of 5. There's our exact value. If I am trying to solve for Z, Z is a leg of the original. So it also is a geometric mean. So it is going to go in the means position between what and what? 25 and 20. The whole hypotenuse is 25, and the segment of the hypotenuse that's adjacent to that leg is the 20, between 25 and 20. So if I do my cross products, what is 25 times 20? 500. I need to take the square root of 500 in order to get Z, which is not an integer. So what's a perfect square that goes into 500? 100. How many times? 5 times. Square root of 100 times square root of 5, well, the square root of 100 is 10. 10 square roots of 5. There is our value for z. So let's try it out down here. See if you guys are very comfortable now setting these things up, hopefully. Let's say I'm going to solve for x. X is this piece right here. Is that a geometric mean position? Yes. Geometric mean position. There and there. Between what? 8 and 33. The theorem says the whole hypotenuse, 33, and the segment next to it, 8. But again, you can take it in either order. So x squared equals, let's not waste our time, get your calculators running. X squared equals 264. What happens when you take the square root of 264? You get an integer. Okay, so I want a perfect square that goes into 264. 4, 9, and participate. Be involved, that's how you learn this. Perfect square. 4 is perfect square, 9, 60. How much? 4 does. Maybe there's a bigger one. How many times does 4 go into it? I'm sorry, say it again. Okay. So this would be 2 square roots of 66. How do I know if I've simplified? Well, is there any perfect square that goes into 66? Well, 11 goes into it, but it's not a perfect square. 33 goes into it. That's not a perfect square. So I know I've fully simplified it. Z. Right there, that's the altitude. That's the geometric mean. Between what and what? 8 and 25. So what's 8 times 25? 200. So what perfect square goes into 200? 100 times 2. So my answer is 10 square roots of 2. Beautiful. 10 square roots of 2. And my last one on this one would be y. Y is also a geometric mean position between 33 and 25. What's 33 times 25? 825? That's probably not a perfect square either, huh? What perfect square goes into 825? Well, 25 does. How many times? 33 times. Look where we got the number. So 5 square roots of 33. Is 33, does it have any perfect squares that go into it? No, just 11 and 3. So we know we figured it out. Now this one is a little different. It has my x, y's, and z's in different positions. Tell me something that is a geometric mean. 12 is a geometric mean. It is the altitude. So I need to put 12 in the geometric mean position. Between what and what?
X and 9.
Between x and 9. So when I solve this one, I get 9x equals, what's 12 times 12? 144. Divide by 9. Does it go unevenly? We'll go to a decimal on this one. 16. X is 16. X is 16. Tell me something else that is a geometric mean. Y is a geometric mean. It is a leg of the original. So y is a geometric mean between 16 and 25. 16 and 25. Dot, dot, dot. I'm not going to solve it, but we've got it set up. What else is a geometric mean? Z is a geometric mean. Between 9 and 25. You got it. And then you can cross multiply and solve. You don't have to have your variable in the geometric means position. So don't be confused if the variable is in a different spot. The variable is not automatically a geometric mean. In this case, the 12 was a geometric mean. It's the position in the triangle. Zach wants to order a banner that will hang over the side of his high school baseball stadium grandstand and reach the ground. To find this height, he uses a cardboard square to line up the top and bottom of the grandstand. You see what he's doing when he's standing right over here? He's taking, and it just has to be a rectangle, something with 90 degrees, and he's putting it out as his eye, and then he is moving until when he looks up the top, he sees the top of the grandstand, and then when he looks down here, he sees the ground. That's what he has done right over here. So it can be anything that is 90 degrees, a book or something like that. Okay, he measures his distance from the grandstand. So he measures his distance and discovers he's 10.5 feet away from the grandstand, just straight across. And from the ground to his eye level. So from straight across down to the ground, 5.75 feet. Find the height of the grandstand to the nearest foot. Well, the part he doesn't know is this X, this leftover stuff, right here. Well, notice he has created this special case. The large triangle is a right triangle from that book right at his eye. And this line straight across is an altitude to the hypotenuse. Where is my geometric mean in that relationship? The 10.5 is the geometric mean. So I know it needs to go in my means position. 10.5. It's the geometric mean between just X and 5.75. Sometimes we may need to get the whole hypotenuse, which you would have to add them together. X plus 5.75. We'll eventually do that for the height. Okay, so let's try this. Do our cross products. 5.75x must equal 10.5 squared. Since 10.5 times 10.5, divide by 5.75. Your calculator's running for me. What's the value of x? Say it again. 19.17. So that's x. So how high is the grandstand? X only went to there. We better add our 5.75. How tall is the grandstand? 24 point. So probably better order about a 25-foot man. And he reaches from the top to the bottom. Your book. Where are we? Page 541. Number 1. They start us out simply giving us two numbers and asking us to find the geometric mean between those two numbers. What will I do with those two numbers to get the geometric mean? Multiply them and take the square root. The square root of their product. The square root of 5 times 20. What's 5 times 20? 100. What's the square root of 100? 10. Write your work. That's where we got that answer. Number 2, same idea. If they just give me two numbers and I'm trying to find the geometric mean between those two numbers, I'll take the square root of their products. So what is 36 times 4? 144. What's the square root of 144? 12. They're being too easy on you. 3. 40 and 15. Square root of their products. 40 times 15. 40 times 15, what's that? 600? Is that an integer this time? Nope. So what perfect square goes into that 600? 100 times 6. So when we simplified it, we would get 10 square roots of 6. Square root of 100 is 10, and then square root of 6. How do I know, again, that I am really done simplifying it? When I look at that 6, what am I looking? Any perfect square. Does any perfect square go evenly into 6? No. 4 is the only one that's smaller. And it doesn't go evenly to 6. Number 4. Write a similarity statement identifying the 3 similar triangles in the figure. We are going to write this all in one statement. So I'll show you how to do it all in one statement. Let's start with the whole triangle, and I'm going to start in the order C. Oh, your book didn't do it in the whole. Well, I'm going to do the whole statement first. I'm going to start in the order E, C, D. Triangle E, C, D is similar to triangle. Now let's go to the left. What would match up with that E? E would have to match up with the E. Now let's look for the C. What was the C in the original? It was the right angle. So what's the right angle in the left one? F. E, F, and then it's easy once you get two letters. What's the last one? C, which is similar to triangle. Now let's work on the one on the right. What goes with E? C. I had to get my bearings here. C would match. And then, what was it? The right angle that came next? So it'd be C, F, and then D. C, F, D. There we have one similarity statement that takes care of all three triangles. The original one, and then the two little ones that are made. Number 5, they want us to find X, Y, and Z. Well, let's start with that X. Is it in the geometric mean position? Yeah. Geometric mean between what?
3 and 5.
It's the geometric mean between what values? 3 and 12. 3 and 12. Pick your order. 3 over X, X over 12, or 12 over X, X over 3. So this would give us X squared equals, what's 3 times 12? 36. What does X equal? 6. Square root of 36, which is 6. So that was nice. Nice integer. How about the Y? Is it in a means position? Yes, it is. Between what numbers? 3 and 15. The segment of the hypotenuse next to it and the whole hypotenuse. So that would be Y squared is, what's 3 times 15? 45. So Y would equal the square root of 45, which is not an integer. What perfect square goes into 45? 9. 9 times what? 9 times 5. So what's the square root of 9? 3 square roots of 5. So it gives us practice simplifying our radicals. How about Z? Is it in the means position? Yeah. Z is also in the means position. Between 15 and 12. What's 15 times 12? 180. Hey, we did this a minute ago. So Z is the square root of 180. What perfect square goes into 180? 36. How many times? 5 times. So this simplifies to 6 square roots of 5. Problem 6. Okay. Tell me something in the means position. 16. The number in this one is in the means position. 16 would be the geometric mean between 8 and X. So this one, 8X equals 16 squared. Then we can divide by our 8 to isolate our X. We'll go to a decimal if it doesn't come to an integer, since this isn't involving a square root to simplify. 32. Well, how about that? 32. Okay, something else that's in a means position. Y is in the means position. So I'll set up a proportion. What is Y a mean between? Okay, X, which is what? 32. We just figured out what it was. 32 and 40. The whole hypotenuse. 32 plus that 8. All right, we may get a square root on this one. Y squared equals, what's 32 times 40? 1280. And when you take the square root of that, my guess is it's not an integer. So what's a perfect square that goes into 1280? The goal is the biggest one. If not, we'll just keep simplifying until we're done. Well, 40 is not a perfect square. It may go into 1280. You may even want to make a list of those perfect squares on your paper. 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144. What number? Oh, I heard a 256. Now, you might have started with a 4. How many times does 256 go into it?
5.
5 times. What's the square root of 256? 16. 16 square roots of 5. Now let me take this and use that 4. Some of you did not think of 256, but you thought of 4. Let's see how that would work. If I thought of a 4, well, how many times does 4 go into 1280? Specifically, since we're in math class, a bunch won't work for us. 320 times? Okay, well, that would be 2. Well, 320. Any perfect square going to 320? I bet there is. What number? I mean, look, use your calculator. So staring at me, 20 is not a perfect square. Does 16?
Yes.
How many times does 16 go into it?
20.
20 times? What's the square root of 16? 4. 2 times 4 is 8. Now, unfortunately, 20 has a perfect square that goes into it. 4. How many times? 5 times. What's the square root of 4? 2. What's 8 times 2? 16 square roots of 5. If you don't find the biggest one, it means you have to just keep going until you can't find a perfect square that goes into that radicand anymore. And you'll still get the same answer. It will just take you more steps. But that's how it works. We have another letter, don't we? Z. Is it in the means position? It is. Z's a leg, so it's in the means position as well. It's the geometric mean between 8 and 40. That segment next to it and the whole hypotenuse, which would be 40. So we have z squared equals 320. Oh, we've seen 320 a minute ago. Let's see if we can go a little faster. In other words, a minute ago, 16, it did go into it, but there must be a bigger perfect square than 16. If not, we'll go with that one. I mean, if you can't think of it, it's there. Oh, 60 is not a perfect square. 64. How many times does 64 go into 320? 5 times. And what's the square root of 64? 8 square roots of 5. If you think of the biggest perfect square, you can do it in one step. If you don't, well, you just keep going until it's fully simplified. Number 7. Number 7. Corey is visiting the Jefferson Memorial with his family. By the way, if you haven't figured it out, we just found a new way to estimate heights. He wants to estimate the height of the statue of Thomas Jefferson. You don't even have to have a shadow. Corey stands so that his line of vision to the top and base of the statue form a right angle. So he'd use something like a book or a piece of paper. And they want to know about how tall is that statue. So look at the diagram. Do I know a geometric mean value?
Hypotenuse. From hypotenuse.
Where's the geometric mean value?
8 foot 8 inches.
The 8 foot 8 inches is the altitude of that big right triangle. It's a geometric mean. Now, 8 feet 8 inches, we need to not mix our units between feet and inches. 8.6 How do I know? Or, yeah, let's go to a fraction maybe. How many inches are there in a foot? 12. So what I have is 8/12. 8 inches out of 12 inches, what does that reduce to? 2/3. 8 2/3 feet. 8 2/3 feet. So there's my means position for that altitude. It's the geometric mean between what and what? 5 foot 8 inches, which would be the bottom part of that big hypotenuse. So 5 feet 8 inches would be 5 2/3 feet again. And x. Let's call the top part. Here is my original right triangle. That hypotenuse out there is the statue. So we knew the altitude was 8 feet 8 inches. Whoops, not 8.8. 8 feet 8 inches. 8 feet 8 inches. And we knew 5 feet 8 inches right here. So we're just calling the rest of that height x. Okay? Now when I do this, I'm going to work with improper fractions. So I'm going to take this 5 2/3, but that is how many thirds? Improper fraction. 17/3. 3 times 5 is 15, plus 2 is 17. I have 17/3 x equals, now 8 2/3, I want an improper fraction. 26/3, and that would be squared. 26/3, that would be squared. And if I want to get rid of that 17/3, how would I get rid of that 17/3? Multiply by the reciprocal. So here's the math that you need to do. Reciprocal is 3/17. We'll get some sort of fraction. 1 9/17. Yes? No? Anybody else? I don't know. Is that right or not? I'm a little worried about that one. That'd be an awfully short statue. Try that again. 26/3, you square that, times 3/17. I'm going to do this by hand before you guys are doing it on a calculator. Can you give it to me in a fraction? Does your calculator work with the fraction? I'd like it in a fraction.
13 and 13/51.
13 and what was it? 13/51? Okay. So all I need to do is figure out, what is this? I want to convert it to inches. Take your 13/51 and multiply it by 12. How many inches do you get? Or I shouldn't have said how many inches do you get. That's what part of a foot it is. 13/51 times 12. What do you get? I didn't want to do that times 12. 13 feet. No, that's not right. Times 12. Times 12. You're not giving me the right answer. What is it? 3.05?
Yes.
Oh. You guys were giving me the right thing. This is how many inches it is. 3.05 inches. It's approximately 3 inches. 13 feet, 3 inches. Now we're going to have to add something to it. We want the height of the statue. 5 feet 8 inches. We're going to have to add to it. So that would be 18 feet, 11 inches. There's our approximate height of our statue. So right over here, I converted that last fraction to how many inches? Approximately 3 inches there that we could add to the end. Your assignment from 541 is 1 through 14, 19 through 32, 36 through 38.